cold right now. My hands, I can't even feel them.
I know, my face is like so numb. It's so cold.
Oh, you know what'd be really good right now?
What?
A hot pack.
You're so right.
Right? Have you ever wondered how it works?
Yeah, like it's so cool how it just like crystallizes. I wonder how it works.
Yeah.
When we think about an instant hot pack, we should first consider the contents of the pack. Here we have some gel-like fluid as well as a metal disc. In most instant heat packs, such as the one we are observing, this gel-like substance consists of supersaturated sodium acetate, NaC2H3O2, and water.
Sodium acetate is a salt that possesses the ability to be supercooled, which means that it can exist as a liquid even below its freezing point, which is approximately 150 degrees Fahrenheit. Since this liquid is able to exist and be stable at room temperature, we can use this characteristic to our advantage to create products like heat packs. However, in order for the liquid to crystallize, a site of nucleation is needed.
When you click the metal disc, the sodium acetate crystallizes in seconds, originating from wherever the disc is. This effect is called nucleation, which is when the molecules in a liquid gather into tiny clusters that resemble the crystal structure of the solid. Specifically, heterogeneous nucleation occurs when the liquid crystallizes around a nucleation site, which is what happens in the hot pack around the metal disc.
The reason why heat packs work is due to thermodynamics of the reaction. The crystallization of sodium acetate is an exothermic reaction. This means that the system of sodium acetate releases heat into the surroundings as it becomes a solid. We can model this reaction using an equation. NaC2H3O2 solid plus 3H2O liquid yields NaC2H3O2, 3H2O solid, and heat. The products of this reaction are sodium acetate trihydrate and heat, which means that the change in enthalpy of the reaction is negative, since the energy released when the bonds form to create a lattice is greater than the energy absorbed to break the existing bonds. Since the reaction is exothermic and we act as a system surroundings, we feel heat from the pack and absorb the heat which is released from the reaction.
From this, we also know that dissolving sodium acetate trihydrate in water, which is the reverse reaction, would have a positive enthalpy and be endothermic, since the energy used to break the stronger intermolecular bonds is greater than the energy released by forming the weaker bonds. This is the reason why you can boil a crystallized hot pack in water to redissolve the sodium acetate trihydrate and return it to its original gel-like state. In this case, heat is a reactant and drives the reverse reaction to occur. Because of this property, you can reuse the hot pack multiple times.
Oh, so that's how it works.
Oh my god, are you okay?
Yeah, oh my god, wait, I think I sprained my ankle. I think I need something for this.
What about an instant cold pack?
Oh my god, yeah, wait. How do those work?
While we previously focused on instant hot packs, thermodynamics and the varying properties of different materials also allow us to take advantage of endothermic reactions that are the mechanisms of cold packs.
In the instance of a cold pack, if we look inside, we would see water and a smaller component filled with ammonium nitrate. This differs slightly from the hot pack, since instead of a metal disc that sparks a reaction, we simply squeeze, hit, or bend the pack to cause the water and ammonium nitrate to mix.
The reaction between ammonium nitrate and water is endothermic. This means that the cold pack system absorbs heat from the surroundings as the salt dissolves. The chemical equation for this reaction is NH4NO3 solid plus water plus heat becomes NH4NO3 aqueous. The change in enthalpy of the reaction is positive since the energy absorbed to break the intermolecular bonds between water and NH4NO3 lattice is greater than the energy released when the bonds between the salt ions and the water form. Since the reaction is endothermic, the system absorbs heat from us and we feel a cooling effect.
From both the heat pack and the cold pack, we can see how thermodynamics plays a role in products essential to everyday life. By utilizing the properties of different materials as well as their reactivity with water, we can see how much materials can absorb or release heat to create a cooling or heating effect as desired. Whoa, that's so cool,
Right?
You know, I never thought of it like that.
Me neither. I guess after taking applied chem with Dr. Bragg, I can see the chemistry in everything.